me this opportunity to talk about some of the work. I should admit that some of these things have been going on for almost 2 years, and I think maybe some of you have seen this 2 years ago when we all met at the Simons Institute. Um, so I bring a new perspective to this interesting large charge approach to conformal field theories. I'm basically a lattice field theorist. So what my goal would be to sort of explore some of the predictions that the large charge community is making using lattice field theory, right? So we have been doing this calculation. An important collaborator is Debashish, but then before that, Suzanne and Domenico were involved in the O2 and the leading O4 model calculations. But Debashish and I have been trying to push the subleading charge sector. I would say we have run into a lot of interesting, I would say, numerical challenges. I will mention briefly about them. But then I think we are at the moment more confident in our results, and I'd like to tell you something interesting about them at this point. So let me begin by giving you a brief outline of the talk that I have in mind. First, I'll give you a brief introduction, which is, of course, I think something that most of you are familiar with, but for my purposes, it would sort of set the notation, the kind of calculation that I'm going to be trying to do. And so that will be helpful, at least for people who have not seen this before. And I'm assuming that a few of you have not seen my talk before. And then I will talk a bit about the O4 model in the traditional approach from the lattice field theory side. And then I will try to remind you of the large charge predictions that have been done within the context of, I think, this kind of model. Then I will introduce a new type of O4 model, which is what we have been using in the past. And I think this model is somewhat interesting from its own right. And I explain to you what that model is. And the reason I have to go through this detail is because later on I'm going to explain to you how we actually get to the subleading charge sector, which is not sort of obvious what kind of calculation we should do in the traditional model. So I will explain that using this O4 model. So I'll introduce this model, and then I will briefly review the leading charge sector that is already now published. But then I will then explain the technical details, which I think I've missed. I did mention it in that talk 2 years ago, but I will explain it in a more greater detail here, hopefully, explaining what our calculation is, and then I will present some results and conclusions. So please stop me if there are anything that I say is a bit confusing, so that we can go. I think I should be done in an hour, so we'll see how that goes. Okay, so let's begin with the perspective from a lattice field theorist. So conformal field theories are very exciting from a lattice field theory point of view because they arise at what we call critical points from the lattice field theory approach. And at these critical points, they are characterized by dimensionless numbers, right? So the first interesting calculation we all do is a 2-point correlation function of a particular operator with some global charge. So I'm going to be only interested in global charges, not spin and other space-time charges at the moment. So if you think about just a global charge, then these 2-point correlation functions decay because there is no scale at the critical point. And these dimensionless parameters dq are what we call the conformal dimensions of these operators with that charge q. So of course, we would like to then have an analytic approach to these, to calculating these dimensionless numbers. But in most cases, there are no small parameters. And that's one of the reasons why a non-perturbative approach would be very interesting. And of course, the the approach that I will bring to the table is this Monte Carlo method. There are other analytic methods that are being developed, and so it'd be nice to know if these methods can also be then compared perhaps with Monte Carlo, and maybe we can learn some new things. Of course, there are perturbative methods, and this is one of the perturbative methods that we would like to explore and see how well it does, right? And so that's the goal of this workshop. So from my perspective, one of the interesting large charge predictions was this fact that a conformal dimension that we can calculate has a very simple form, right? It can be expanded in powers of q, and of course it depends upon the dimension. I'm going to be interested in three-dimensional conformal field theories, so that's why the leading q dependence goes like q to the 3 halves, and then the next one is q to the half, and then of course it keeps going down. Interestingly, there is this constant that we just also talked about in the last talk, and this can sometimes be calculated analytically. Sometimes perhaps there is a log q part in this particular case, but I think in 3D the belief is that it's just a constant. And so the C3 halves and C halves are, of course, depends on the theory, so it's sort of a low energy constant. C naught is universal, and then of course there are these higher order terms. The goal, of course, from my perspective is to understand how well does this prediction work, right? How small a charge q that one can use in this expression to still get a good approximation of d of q if you drops, let's say, higher order terms, right? And so our goal is to compute d of q and then compare it with this particular formula. Now, one of the challenges that we have in a calculation of d of q is that the Monte Carlo methods, at least the traditional ones, and maybe even other ones that I will talk about, suffer from what we call a severe signal to noise ratio. And sometimes it's also called a sign problem. I'm sure maybe some of you are familiar with this issue for many lattice field theory problems, including the theory of strong interactions, where we are unable to understand the phase diagram of theories when you have chemical potential. So in a sense, since we are introducing charges, it's sort of analogous to introducing a chemical potential, especially in the large charge sector, and so it's not surprising that there will be some kind of issues like this. And so one of the challenges we have been facing is to sort of beat that, right? And I'll explain to you what we do. So let me now begin with explaining the traditional approach to this problem, and then we'll see why we might need another approach to think about the large charge sector. So in the traditional model, what one does is begin, of course, we are interested in an O4 model. That's the model we are going to be thinking about. So on each lattice site, so now it's a 3D lattice, but for artistic reasons, I'm just writing a 2D lattice here, but it's supposed to be a 3-dimensional Euclidean lattice. And each site has a 4 vector. So this vector phi of x is a 4 vector. And then you integrate over, so it's a unit vector, so you integrate it over that unit sphere with a very simple traditional action. And you can easily convince yourself that when beta is very small, these phi's fluctuate randomly because there's no action for these phi's, and so you are in some disordered phase. But when beta is very, very large, you like the phi's to be aligned, and so you are in some kind of a ferromagnetic phase. So the lattice model actually has a very nice phase transition between the disordered and the ordered phase. And that phase transition is second order, and that the physics at that second order critical point is supposed to be a conformal field theory and describing the Wilson-Fisher fixed point. And so our goal would be to tune ourselves to this beta C and then ask what is the properties of this conformal field theory at large charges. So what does large charge here mean, right? Since it's an O4 model, the charges are characterized by the representations of O4, which is basically the same as SU2 cross SU2. And so there are two SU2 sectors, the left and the right sectors, if you wish. And so given a sector JLJR, that is what Q means. And we can actually compute the conformal dimensions in each of these sectors, sitting right at that point. And so the goal would be to calculate some 2-point correlation function in a fixed charge sector, right? So these phi OX and OY are basically fields that are constructed out of my fundamental field on the lattice, which is phi of X, which is a vector, 4 vector. And then I look at the 2-point correlation function, pull these X and Y far apart. So I need large lattices. And then as X and Y are pulled apart, this, if I sit exactly at beta equals beta C, this quantity is supposed to go at least a decay like a power law, and if I can actually compute that accurately, I should be able to extract this D. That would be the goal. Now, of course, constructing this operator in a given charge sector is not easy, because now I have to do group theory of SU2 cross SU2. Although analytically it's easy, when you try to do it on the lattice, you have all kinds of combinations of these phi of X, superpositions, if you may. And then you have to construct operators in that sector. So just to give you an example, the leading sector, of course, is half, the smallest charge sector is half-half, and that comes from the field itself. It's a vector representation of O4. So in the JL-JR space, it's half-half. Now I can take two of those and construct more interesting operators or fields on my lattice. And of course, if I take a tensor product of the two vectors, I get a superposition of all possible J sectors. And now I need to project out one of these, if you wish, right? So for example, if I want to project out the 1, 0 sector, I will have to take the right Klebsch-Gordon coefficients and combine the tensor product. And this is something that we all appreciate. So these Klebsch-Gordon coefficients, of course, will have positive and negative contributions, right? And now you can imagine that if I put this in and try to calculate the 2-point correlation function, I will get combinations from different kinds of tensors, right? And then I'll have to sum them up in the appropriate way to get the right projected correlation function. Generically, as JL and JR become larger, you can easily imagine I need to project with a large tensor product of all the different phi's, right? And project it to the right space. And you can easily imagine this combination to have lots of interesting cancellations. So of course, if you could do that calculation, the predictions would be the following, right? And this was nicely shown in this paper. So the DJJ, the leading sector, this is what we studied some time ago, goes like J to the 3/2 times a coefficient, and then J to the 1/2 times another coefficient, plus this constant, and then of course the leading or other higher order corrections. So this is what, when JL and JR are the same with a given J and J becomes large, this is the leading charge sector. Now what I mean by the subleading charge will be to compute this D of J, not JL and JR are not the same, but one off, right? So one is J, the other one is J minus 1. Right? In that case, just last year, a nice prediction came for this particular quantity, which basically said that you get the same djj minus 1 is the same as djj, plus there could be some term that actually goes to 0 as large as j becomes large. And that is a new low energy constant. And then, of course, there are higher order terms. Now, initially, I think in our work, we had assumed that there would be maybe another constant piece, but this prediction suggests that there is no such constant. And so the interesting prediction from my perspective is that this difference between j minus 1 and jj is actually something that goes to 0 as j tends to infinity. And so that would be interesting to compute and see if that matches. So that was our goal. So let me briefly tell you that if we wanted to use the traditional approach, we will get into problems, right? And this is exactly the cousin of the sign problems in lattice field theory at a finite chemical potential. So we know that when L and Jr are large, this dimension becomes large, which means that if I try to calculate this 2-point correlation function, it is going to decay quite rapidly. Remember, this d is very large, so this is going to decay very rapidly. So that means when x and y are very far off separated, this quantity is going to be small. But then if you think about how this calculation occurs, these are all field variables, which are all unit vectors, right, to begin with. And so these are all quantities of order 1. Sorry about that. These are all quantities of order 1, right? So we need cancellations of order 1 to get a really tiny number, and which is not very easy to obtain. And so even numerically, you get into a lot of trouble. So clearly a new approach is desired. So for that reason, we started thinking about a new way to think about this O4 model. And now it has become clear to us as this new approach, which was just a practical thing for our calculation, actually has a deeper understanding or leads to some deep way of thinking about field theories in itself. And so I wanted to spend a few minutes explaining that. So if you think from a quantum mechanical perspective, what the traditional lattice model is, the Hilbert space is actually infinite dimensional at every site, right? So to see that at each site, we had a 4 vector, right? And it was a classical number, but that's because we wrote the whole thing in a path integral language. Now, if you go back and ask yourself, what is the Hilbert space on which this path integral was constructed, there is actually eigenstates of an operator phi of x, and these eigenstates form a complete basis, and it's an infinite dimensional space, right? So you integrate over all unit vectors, and then you get the identity. Now, of course, there is a conjugate basis if you wish. This is like position, then there will be angular momentum if you wish. And so in the O4 case, the angular momentum is naturally represented in terms of an L, and then M1 and M2 goes from minus L to L, right? So that's the natural basis of these states. And so there is an identity in that space, right? And L goes from, unlike for the O3 case, here it goes from 0, half, 1, 3 halves, and so on. And for every L, M1 and M2 goes over minus L to L. So the qubit regularization of a field theory essentially is a way of writing down a lattice model. Instead of that model living in this infinite dimensional space, it lives in a finite dimensional space at every lattice point. So notice this is a Hilbert space at every lattice site. So every spatial site, if you wish, has an infinite dimensional space, infinite dimensional Hilbert space. And then, of course, the Hamiltonian then evolves it in Euclidean time. But you can ask yourself, are there models in a finite dimensional Hilbert space that you can actually achieve the same conformal field theory? Right? And if you can, then you would say that you have a qubit regularization of that lattice field theory. The reason this approach is very interesting these days is because there's a push, at least from some community, to be able to solve quantum field theories on a quantum computer, and that would be very natural if you could write down this in a finite dimensional space. And what we then realized was this: the approach that we are exploring is actually exactly that. So the simplest qubit regularization of the O4 model will be a 5-dimensional Hilbert space. So that will involve the L equals 0 sector, right? That will be like a singlet of the O4. And so we'll call that as the Fock vacuum, if you wish. And in our approach on the lattice, we will label this as a single state, which we call a monomer. It's exactly a 0-0 state, a Fock vacuum. So we're going to build a lattice field theory with these states, which is like a single dimensional Hilbert space. And then, of course, we're going to, that alone, of course, is going to be trivial. We won't get any physics out of that. So we need to add something more interesting. And for that, we write the L equals half. Remember, that was the next state in our, if you wish, the low-lying angular momentum states. So L equals half. Of course, it's a 4 vector, so there are 4 states. M1 is plus or minus half, M2 is plus or minus half. So that we will represent by it's of course an SU2 quantum number for L and R. So we can represent it by the Z quantum number, QLZ and QRZ, right? And both of them are plus or minus 1. That's the O4 vector. So it's like a half-half sector. And so when we think about our lattice, we will think about it in the following way. We're going to think about vector particles, and these particles are going to be are vector particles, so they're going to conserve the O4 quantum number. And so we give them, so these are the Z component of charges, so half-half, and then there'll be a minus half, and these are, we call the red particles, if you wish. And then there'll be the green particles, will be half minus half, so the JZ is still half, JLZ is half, JRZ is minus half. Right? And so this will be the minus component of that. So then if you write down the partition function in this 5-dimensional Hilbert space, the partition function just becomes a loop gas, right? So notice, these are the Fock vacuum states, these blue dots, these are what we call the monomers. And then these red loops or the green loops are the O4 particles, right? And so if you write down a simple model, which is O4 invariant, one of the simplest models will be this model. And it's also space-time rotationally invariant, right? So it's like a space-time lattice model that also has the same physics as the usual traditional O4 model. The traditional O4 model lived in an infinite dimensional Hilbert space. This lives in a 5-dimensional Hilbert space. The partition function is pretty straightforward, at least in this simple case, where we give a weight U to these monomers, right? So every time you have a monomer on a space-time lattice, you get a factor of U. So then, and that's it. That's the only other weight. In addition, of course, there are the constraints, which are these O4 constraints, that they should all come in loops. And each loop can have 2 orientations. And then there are loops itself can be either red or green. And all of them have equal weight, right? So if you, for the moment, integrate over the O4 field, every loop will have 4 orientations. It could be either red or green. It could have 2 different orientations. So one of the interesting outcomes of this thing is that, as you will see, the large charge sector becomes very easy to study, because we can use a new technology which has been developed over the last 2 decades or so now, which are called the worm algorithms. And we can sort of create change loops, right? Create monomers and dynamically update our configurations, and they are very efficient.
Shailesh, can I ask
Yes.
you a question?
Sure.
So I know that for algorithm, supposing we're using Metropolis, just to have an idea of how things evolve. How would this thing evolve? So say you have this in here. So what's the next Metropolis step here?
Yeah, very good question. Metropolis steps are very bad for these algorithms, so don't even try it. Because that's one of the reasons. So this is a very good question actually. Historically, these type of world line methods were discovered, I would say, in the 1980s, but they were never useful for lattice calculations because of exactly your question. So if you try to do a metropolis, for example, I could take a placket here, and I could notice I could make the red thing go like this and go like that. So I can change local plackets and try to make some local moves. So metropolis algorithm is there, but it's very inefficient because only moves that can be done are very local, and that too often, because of these constraints, they'll be forbidden. You cannot do something. You can propose, but the algorithm says, sorry, I'm not allowed to do that. You propose, sorry, you're not allowed to do that, right? So very few places in your lattice you'd be able to make this move, right? Another thing is, remember, these are world lines, so there's topology of these world lines. Especially if there are identical world lines, there are things that exchange. A metropolis will never be able to change the topology, so you will not even be ergodic in your calculations. So if my suggestion is, if you're trying to use this, do not use metropolis, although you could try it, but you'll just be doing the wrong physics. And that was the revolution that the worm algorithms allowed us to do.
Okay, thank you.
So the worm algorithms, actually, the reason they are very efficient is because they do not live or work only in this configuration space. You allow yourself to go out of this configuration space by introducing sources and sinks, as I will mention in a minute. So for example, if I wanted to calculate correlation functions, right? So here is a creation operator and an annihilation operator, right? So a particle can be created and annihilated. And this is the sector in which the worm works. So this is actually a worm, right? So what you do is, in your calculation, you allow yourself to create a creation and annihilation event, which is not part of the partition function, but it's a very interesting observable to measure. And then you do a Monte Carlo. In fact, now you do a metropolis, right, locally, and you move this. For example, I could move and eat up this monomer and put a red line there, right? And then I could go up, And now if I came here, of course, now there are various ways of doing it. I could change this loop into a red and then move in, right? So you can do all kinds of clever tricks. And so you can actually change this loop to a green as I move and then come back and close, right? So I can do all kinds of interesting things with the worm algorithm, right? So these correlation functions are very easy to measure. In addition, one of the nice features of this approach is that you can easily, you're working in a basis where O4 charges are conserved. So you can actually measure the O4 charge. So for example, you could take a time slice, right, and then see what is the charge in that particular time slice, because this is like in the diagonal basis of charges. So you can actually measure the charge that is flowing in this direction or in this direction. So there are many observables we can measure, and one of the, of course, the observables that we initially measured was the susceptibility, and then the winding number, which is basically the square of the charge in a given sector, right? And so you can easily even convince yourself that there is a very nice phase diagram that, for example, when U is very, very small, there are no monomers in the system. right? So everything is like in a vector particle state, and that is in a broken phase. Actually, it's a superfluid of the O4. Um, on the other hand, when U is very, very large, the whole lattice is filled with monomers. So there is no vector. Vector-like particle is very massive. So this is like the massive phase. This is like a broken phase. And so there is a critical point. And so one can ask, what are the physics near that critical point? And so the traditional model, of course, has been studied very nicely at that critical point, and you know what the critical exponents are. And what we did was we did the same calculation. We get very nice. We know where UC is very accurately, and you can actually see that the numbers match very nicely between this qubit model and the traditional model. So this gives us confidence that this qubit model is actually is in the right universality class of the O4 traditional model. But the interesting feature now is that we can actually do the leading large charge sector, right? So the goal now is to create these sources and sinks in a given JLJR sector, and then study how they decay at large L's. So what we do is we put them on a L cube lattice. They put them at an L by 2 separation, exactly like midpoint between the two, and then we pull the lattice size very, very large. Of course, the goal is to construct the right sources and sinks with the right quantum numbers, which is not very difficult. But what we found is that a fermionic representation of our model is very helpful. Remember that our model is a discrete model. So in some sense, maybe there's a fermionic description of this model, right? And indeed there is. So here is the fermionic representation of our model. So on each site, we introduce 4 Grassmann fields, right? This is to represent the 5-dimensional Hilbert space. There'll be 4 Grassmann fields. And you can easily imagine that the 4 fields will be like, in fact, it will not be this 4 field, but there will be bilinears that we can make, right? And these bilinears will then be like, if you want, from the perspective of strong interactions, these will be like pion fields, right? And these will be the fields of that will encode the physics of O4. And then the partition function itself is very easily written in terms of a fermionic action. And the fermionic action actually is very reminiscent of, if you wish, 2-flavor QCD, right? It involves this matrix, a 2 by 2 matrix. It's like trace of M. Instead of M dagger, I'm just writing it as M, because you'll see that the properties of M is very naturally encoding the O4 symmetry. And then I have a determinant of M, which is also O4 invariant. And so these are the 2 fields that I write down. So it's invariant under SU2 cross SU2, exactly like how one would write down a pion field that is being invariant under SU2 cross SU2 symmetry. And then the action is invariant under this, is easily readable from this. Except that there is an even odd kind of difference in this approach, which is very, very familiar with people who do QCD with staggered fermions. And so there, the even and odd lattice sites are treated differently. And that comes about very naturally in this case. In fact, long ago, I wrote a paper on this with my student where we studied strong coupling U1 gauge theory. And there the physics was almost identical to this. So once we have that, now all we have to do is to write down the proper correlation function. We know how these lattice fields transform, so it's easy to build the right operators in terms of these Grassmann variable objects. So this will be the source, that will be the sink. So let me be a bit more explicit as to what JLJR are. So I'm going to put in a new quantum number. Remember, for every JLJR, there is an ML quantum number and MR quantum number. And so there are lots of operators in the same sector. Of course, all of them are interchangeable because of a symmetry. But in a sense, there are many operators that we can use to actually do the do the 2-point correlation function. So for example, if you take single sites, sources, the half-half representation, you can write down what it is in terms of Grassmann variables, right? The minus half is another Grassmann variable. You can work this out. If it is half minus half, then even and odd sites are different, and odd and even sites are different. Again, it's minus half and half. And now you can, once you have the sources, the sinks will be in the conjugate representation, so you can work that out. So now let's take this Grassmann representation and map it to world lines, because it's much more visual in the world line language. So in the world line language, if I had a red source and a sink, I would say this, it's a source of a half-half and the sink of a half-half, right? So it's like a half-half particle was created and annihilated. If it's a green world line, there will be a half minus a half, right? It's like a different, it's still half-half quantum number, JL, JR are half-half, but then it's like the M component is different. And then it's the conjugate of that. And so now we can build in higher JLJR by putting many of those together, right? So basically tensor product of these half-half representations. Now the highest weight representation JJ, right, and ML is equals J and MR to be J, can be obtained by putting all reds, right, because everything is half-half. So just put a bunch of reds and you will get the highest weight representation, and that will be JJ. So for example, the JJJJ operator will all be sources of the red world lines. Now of course we cannot put all of those on a single site because of this qubit problem. So what we do is we distribute it over a spatial slice. So for example, the first source is here, the second source is here, third is here, fourth is here, and so on. So for 2j equals 20, that's our source, right? That's how we put the source. Notice I've left the middle site empty, and you'll see in a minute why I do that. So what we do is we put a source of this type at t equals 0 and a sink at L by 2, right? T equals L by 2. So the algorithm is pretty straightforward at this stage. You put a source and a sink, right? And then, as we will see in a minute, we'll create a new worm, a source and a sink in the middle. Remember, I left the middle site empty. I can add one more particle if you wish, right? The reason is because if you want to calculate this kind of correlation function, as I mentioned, this D is very large and this decays quite a lot. So it's very hard to pull them apart. As I make L larger and larger, to really do this calculation by introducing sources and sinks is not very easy. However, worm algorithms can efficiently compute ratios of such correlation functions. And so that's exactly what we are doing here. So I will be in a J-1 sector, and then I add one worm and create the JJ sector. So this will be the ratio of two partition functions, which is precisely what the worm does. It creates a partition function without the worm. On that, it creates a worm, which is another sector. And that's precisely what you're trying to do. And so this is like a 2-point correlation function, if you wish, on a background sector, right? And that we know how it decays. And from that, we can actually compute the difference in dj, j and dj minus 1, j minus 1. And that we can fit to this form, right, and get the things. So these are some of the results, which is actually a review, so I'm not going to go into it. We have already published this with Domenico and Suzanne. And this leading sector prediction works beautifully. So here is the result, right? So what we were able to do at that time was be able to compute the C3 half and C half, and this prediction works even at the smallest q extremely well, right, within 1% or so. Now the goal was to see how well things happen in the subleading sector. So in that case, what I need is to construct a source that is jj for the left and j minus 1, j minus 1 for the right. This is again the highest weight sector in the jj minus 1, right? How can I do this? Well, to begin with, we know when all the things were red, we were in the jj sector, right? So if I flip one of the sources to a green, right, green world line, then I change the jz r to minus a half, right? And so I reduce the jz by 1, right? And so if you think about what this operator is, I call this as OL, where I change the Lth source. I call it half, 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 half. They're all red, they're all half, half, but the green is half minus a half. So from the perspective of just SU2 group theory, the R, the Jz quantum number of R is 1 less here, right? And so I can actually not construct this easily, but I can construct jj minus 1 as just a linear combination of all such operators where the green is at every such site, right? So I take my source and I imagine each of my sources to become a green, right? And then I have to add up all of those OLs equally. That will be J, it'll still be the leading sector, but then the JZ quantum number will be J minus 1, right? But that's not what I'm interested in. I'm interested in the JR to be J minus 1. So it should be an orthogonal combination of this, right? So that clearly shows that we need to introduce some phases, right, to be able to get an orthogonal combination of this. Well, in a most democratic way, we know that there are 2j minus 1 orthogonal superpositions, right? Because it's like 2j charges. I can make all kinds of superpositions which are orthogonal to that, and all of them will be in this sector, right? And so I label the 2j minus 1 orthogonal superpositions with this variable m, and then these are just some phases which make them orthogonal, right? So it's easy to work out how to construct the orthogonal superposition for OL. So similarly, once you know the source, I can construct the sink as the conjugate representation of that, right? So here I have a set of 2j minus 1 sources and 2j minus 1 sinks. And I can choose any of them to create my the correlation function.
So just one question. Why don't you just pick one OL? I mean,
yeah, I'm going to come to that in a minute. It's a good point. So I can pick any of them, right? But then, of course, I can pick any matrix, M prime, right? But notice these are all phases, right? To do this calculation is very non-trivial, at least for the computer. I have to do lots and lots of additions and subtractions. Can we do something analytically here? Well, we can do exactly what you said, Domenico. We can choose the diagonal sector, right? And then add them up, right? M equals 1. So this is basically the trace of that particular matrix. And that has a very easy form. We can actually do that calculation exactly, right? And so that calculation involves, if you actually work it out, it involves actually the correlation between OL and OL bar, or OL, oh, the prime should appear in the L prime here. So OL prime and O bar L. Oh, Simeon wants to admit, I admitted him. Okay. So the worm algorithm again can't calculate ZJJ minus 1, but it can calculate ZJJ minus 1 over zjj. Again, remember, it's ratios of partition functions which are very easy to compute. So this we call r tilde j. And that naturally measures this difference. This is what was the prediction, remember, from last year. It was this delta tilde j, which is the difference between jj and jj minus 1. And that calculation is very easy for us. So what we do is, we do the jj calculation that we have done before, right? So we create configurations with the charge 2j sources and sinks, right? And then what we do is we replace each of these with some OL. That means change one of these with a green line and replace this with OL prime bar. That means replace this with one of the green sinks, right? Clearly, if I replace this with a green and that with a green, that will be 0. Because this is a green means this will be the green, not this one, right? So not all of them will contribute. Only the ones that have the consistent green will contribute. And so then it's very easy to measure. If, for example, in this case, L and L prime are the same, then we get a 1 over 2j. If they are not the same, we get minus 1 over 2j times 2j minus 1. And so here is a simple calculation. So for example, suppose this was a source and a sink in the red for the JJ's configuration. What we do is we change this to a green. Oh, that's like the same JJ. So then we get a 1 over 2j. Then we change this to a green. This is a different source. So then we subtract out 1 over that. We then change the third one. We subtract this out. Then we change the fourth one. We subtract that out. And then we add up all of these. Right? That's our contribution. So in this case, 2j is 4. In fact, if we add everything up, you'll see that I get a 0. So sometimes this is the cancellation I was talking about. So there are cancellations because we are projecting to the subleading sector, but then we can actually still do the calculation. So here are the results. So here is a result for j equals 1. These data is the j equals 1 result. These squares. This magenta circles are j equals 10. And then these diamonds are actually j equals 20. This is actually the largest j we were able to go, and I'll explain to you why. So notice for j equals 20, to get a power law, we needed to go up till 256 calculation, right? So 96, 128, 160, 192, and 256. So these are very big calculations. Unfortunately, this was the main source of time. It took us almost 3 to 4 months to get these two data. And even here, the error bars are slightly bigger than what we could actually get at the moment. And also, what we realized was that because of these cancellations, notice even at j equals 1, there's a big error bar here, right? Of course, this is on a log scale. So this error bar is very small. It's actually comparable to this. But on a relative scale, this error bar is large. And this is one of the sign problems, right? So we still have cancellations even at j equals 1 as we go to large lattices. And so in fact, we had to really learn how to do this calculation without biases, and that took almost 6 months to 8 months, I would say. And then so now I think we are reasonably comfortable with our error analysis. We understand how the critical slowing down is coming in, and I would believe, of course I can't since I've not done the calculation, that this would be almost impossible to do with the current computers with the traditional model. So if you fit these to the form, we can actually extract delta tilde j, right? And these are the fits to the solid lines that I show you here. Also notice that as j becomes large, these small lattices actually don't fall on the right curve. If you make a mistake and just take these values, you might still get a power law, but that power law is different from the power that you get when you go to larger lattices. And so you have to really be very careful, not fit in some intermediate range and extract those numbers. Okay, so here are the final results. Maybe this is not interesting to you right at the moment. I just wanted to flash it. Our paper mostly will come out this week or so. We want to talk to Domenico and Suzanne about it, but these are sort of the numbers that most likely we will publish. This is our latest result. And last time when I gave a talk, I guess it was in June, maybe early June, we didn't have this error completely under control, but now we have. And this was the several month calculation that we had to do. Okay, so let me show you the large charge predictions. Remember again that the prediction was that this constant was 0. This was the unknown thing that was to be determined. And so here is our data, right? And I'm not going to give the 20 result yet. Let me just show you how things looked in June. So this is just to recollect your memory. So this was this 2, 0. So if I allow for a constant here, then the data fits fine in this region. It actually fits to just two, right? A constant and j to the 1 over root j. I think we're just dropping, starting at j equals 3, I think, if I'm not mistaken here. The chi-squared is reasonable. But interestingly, at that point, we could also fit to this form, where we could set this to 0, right? And so we weren't able to, even at j equals 10, we weren't able to distinguish which was the right fit. And so we had to run something at a bigger j, and that's what we ran. And I think I mentioned that this was the error that we had last time, but now we are more confident about this error. And of course, it doesn't quite fall on that line, so one might wonder what's going on. But it's definitely very far from this line, right? In fact, if you try to fit this blue line to this, it doesn't fit. It's a pretty bad fit. On the other hand, if I try to fit this form with this extra point, it fits fine. It's just that this comes down slightly, the chi-squared goes up slightly, but it's still within errors. We can actually see that it's okay. So here is our prediction. Here is our result, right? So the prediction suggested that this was 0. So far, we think, at least for these values of j, c naught tilde is not consistent with 0. Of course, we do have an estimate of lambda squared, which is that. I must emphasize that this is a large j expansion, and we are using a range of j's, and we were sort of quite motivated by our leading charge sector result, which extended all the way to small j, right? It's possible that for some reason this is not true for the subleading sector, and then the real prediction only occurs at very large j's. That's a possibility. So then we'll have to throw away all our data before we even fit the thing, right? So that's always a possibility. But if we believe that, well, these two are reasonably a good, effective description of our data, maybe it's worth thinking about, is there any reason why the c naught tilde is non-zero? So let me present my conclusions. So the recent proposal of the Q expansion of the CFTs continues to be a very exciting approach from my opinion. Maybe there are certain things we need to understand, but it still works quite beautifully. In the subleading sector, we do think maybe there is an extra term, which perhaps is useful to think about. Of course, there's another possibility is that this is only valid for much larger values of Q, where we are not yet there. Now, another thing I'd like to emphasize is that the drastically simple model was very important for us to do Monte Carlo calculations. Otherwise, as I already showed, to go to very large lattices was almost impossible. And so maybe there are some extensions of this to study other CFTs, and that'll be interesting. Let me stop. Thank you.